Okay, so students, we'll be beginning with our third chapter, HCF and LCM. Well, to begin with, we all are aware of the full forms of these two concepts. HCF means the highest common factor, and LCM refers to least common multiple. Before we actually start with the HCF and LCM sums, let us brush up our knowledge of the basic concepts that we have learned. Numbers are basically divided into two types as even and odd. This is what we have learned in the lower classes. Numbers which are divisible by 2 are called even numbers. For example, 2, 4, 6, 8, 10, 12 and so on. The other group of numbers is odd numbers. It involves the numbers which are not divisible by 2. Example 1, 3, 5, 7, 9, 11, 13 and so on. So this is how we divide numbers as even and odd numbers. The other type of classification for numbers is prime numbers and composite numbers. Prime numbers are numbers which has only two factors, 1 and the number itself. Examples are examples are 3, 5, 7, 11, 13 and so on. However, we need to note one important thing here, and that is 2 is the smallest even prime number and 1 is neither prime nor composite number. Moving on to the other type of numbers, that is composite numbers. Composite number has more than two factors. If I take an example like 6 has more than two factors. The number 1, 6 itself, as also it falls in the table of 2 and also in the table of 3. 2 into 3 or 3 into 2 you can say. Yeah, so it has more than two factors. The other examples are 8, 10, 12, 14. All these are composite numbers which has more than two factors. Prime numbers are further classified into two types as co-prime numbers and twin prime numbers. The two numbers which have only one as a common factor are said to be co-prime or relatively prime or mutually prime numbers. Examples are 10 and 21. So this is a pair of numbers which are co-primes. The divisors of 10 are 1, 2, 5 and 10. Similarly, the divisors of 21 are 1, 3, 7 and 21. Now, amongst these divisors of both the numbers 10 and 21, the only common factor for both are just one number, and that is number 1. So 1 is the only common factor amongst the divisors of both the numbers 10 and 21. That is why it is said to be a pair of co-prime numbers. Other examples of co-prime numbers are 3 and 8, 4 and 9, 21 and 22, 22 and 23, 23 and 24 and so on. So these are all co-prime numbers. Let's come to the next type of prime numbers, the twin prime numbers. If the difference between two co-prime numbers is 2, the numbers are said to be twin prime numbers. In order to have examples here, always remember there should be difference of 2 between the two numbers. So if I say 3 and 5, it is a pair of twin prime numbers because the difference between them is 2. 5 minus 3 is 2. The next pair is 5 and 7. 7 minus 5, we have the difference of 2 amongst these two numbers. So this is also a pair of twin prime numbers. Other examples are 11 and 13, 29 and 31. All these are twin prime numbers. I'm presenting to you a method of finding prime numbers from 1 to 100. In your textbook itself, right in the beginning, you are asked a question where you are supposed to find the prime numbers from 1 to 50. So this is how we'll be doing it. Here, however, I have taken numbers from 1 to 100 altogether. So this method is called the sieve of Eratosthenes.
The following steps will help us find the prime numbers. Start by crossing out the number 1. Do you know why we cross out the number 1? Any takers? Well, it's because a prime number is any number greater than 1 and only divisible by itself and 1. So 1 cannot be a prime number because it is not greater than 1. Okay, now let's put a circle around the number 2. It is a prime number because it is greater than 1 and is only divisible by itself and 1. 2 is also the only even prime number. Next, we'll cross out all multiples of 2. To find the multiples of 2, simply skip count by 2. For example, 2, 4, 6, 8, 10, and so on. Did you notice any patterns for the multiples of 2? You do realize I can't hear you. They all end in 2, 4, 6, 8, or 0. So if a number ends in 2, 4, 6, 8, or 0, then one of its factors is 2. Next, let's put a circle around 3. It's a prime number because it is greater than 1 and is only divisible by itself and 1. Next, we'll want to cross out all the multiples of 3. To find the multiples of 3, you can skip count by 3. For example, 3, 6, 9, 12, 15, and so on. You'll notice 4 is already crossed out. That's because it's already a multiple of the prime number 2. The next unmarked number is 5. I'll just place a circle around the 5 because it is a prime number. Next, let's skip count by 5s. Do you notice any patterns in the multiples of 5? I sure hope someone got that. They all end in 5 or 0. So if a number ends in 5 or 0, you know one of its factors is 5. 6 is not a prime number. Do you know why? Because 6 has more than 2 factors. Its factors are 1, 6, 2, and 3. All the multiples of 6 are already crossed out, because if a number is a multiple of 6, it already had factors of 2 and 3. Looking at the table, our next unmarked number is 7. It is prime because it is greater than 1 and only has 1 and itself as factors. We'll circle it and then proceed to mark its multiples. Most of 7's multiples are already crossed out because those multiples have more than 2 factors. 8 is not a prime number. Do you know why? Because 8 has more than 2 factors. The factors of 8 are 1, 8, 4, and 2. 8's multiples are already crossed out because if a number is a multiple of 8, it also has a factor of 2. 9 is not a prime number because its factors are 1, 9, and 3. It has more than 2 factors. All of the multiples of 9 have also been crossed out because they have other factors besides 9. For example, 18 is already crossed out because it has factors of 1, 2, 3, 6, 9, and 18. 10 is not a prime number because it has factors of 1, 2, 5, and 10. All the multiples of 2 and 5 have already been crossed out. This also means that all of the multiples of 10 have been crossed out. Now that we found all the multiples of 2 through 10, all we have left that are not circled are prime numbers. Why are they prime numbers? Remember, because they only have factors of 1 in themselves. Our prime numbers between 2 and 100 are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. So remember, in order to find a number that is not prime, try to see if it is a multiple of another number. And as always, the sieve of Eratosthenes is your safety net for prime numbers. Uh-oh.
So this was the sieve of Eratosthenes, which helps us to find out the prime numbers between 1 to 50, or you can say 1 to 100. Just now we have seen how to find the prime numbers between 1 to 100. So now we are ready and all set to begin with practice set 10. The first sum in practice set 10 says, which number is neither a prime nor a composite number? One is a number which is neither prime nor composite. We have seen it in the explanation some time back, which says 1 is a number which is neither prime nor a composite number. We shall write the answer in a full complete sentence. 1 is neither a prime number nor a composite number. Question 2. Which of the following are pairs of coprimes? 8 and 14. This is the first pair given to us. In order to find the pairs of coprimes, let us just bring to our mind the definition of coprime numbers. Two numbers which have only 1 as a common factor are said to be coprime or relatively prime or mutually prime. Only the number 1 has to be the common factor. So let's go back to our examples. The first example that we have, 8 and 14. These two numbers in fact have two common divisors, that is 1 as well as 2. So 8 and 14 is definitely not a pair of coprime numbers because they have two divisors, not just one. So it is not a pair of coprime numbers. Come to the next example, 4 and 5. The numbers 4 and 5 do not have any common divisor other than 1. So it is a pair of coprime numbers. Come to the next example, 17 and 19. 17 and 19 is a pair of coprime numbers. Come to the last example, 27 and 15. These numbers have two common divisors, that is 1 and 3. Both these numbers fall in the table of 3. So it is not a pair of coprime numbers. Question 3. List the prime numbers from 25 to 100 and say how many they are. We have seen this in the method or the sieve of Eratosthenes. So using that method, we will strike out the numbers which are divisors or multiples of other numbers, and this is how we can have a list of numbers which are prime from 25 to 100. In the sieve of Eratosthenes, we have done the numbers from 1 to 100. So we are just picking out prime numbers from 25 to 100 from that list. So we have 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89 and 97 as the prime numbers between 25 to 100. So if we just count them up, all the numbers that we have here, they sum to 16. So there are altogether 16 prime numbers from 25 to 100. Question 4. Write all the twin prime numbers from 51 to 100. Let's bring to our mind what exactly are twin prime numbers. If the difference between two prime numbers is 2, then the two prime numbers are called twin prime numbers. So in order to have a list of prime numbers between 51 to 100, we should have the difference of two numbers between them. The answer is 59 and 61, and the other pair is 71 and 73. So these are the two pairs of twin prime numbers from 51 to 100, and both these numbers have a difference of 2 between them. 61 minus 59 gives us 2, as also 73 minus 71, here also the difference between these two numbers is 2. So these are the two pairs of twin prime numbers from 51 to 100. Question 5. Write 5 pairs of twin prime numbers from 1 to 50. Following are the pairs of twin prime numbers from 1 to 50. 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31, 41 and 43. So here are the 5, more than 5 in fact. These are the 6 pairs of twin prime numbers that we have written between 1 to 50. Let's continue with question 6. Which are the even prime numbers? The answer to this is 2. 2 is the only even prime number. So here we come to an end of practice set 10. Let's go to the next practice set of this chapter, practice set 11. However, before we begin with the first sum of practice set 11, we need to know what exactly is prime factorization. So first we will just have an overview of what is prime factorization. Always remember, any composite number can be written as the product of prime numbers. For example, if I take the number 45, I can write 45 as 5 into 9. 9 is in fact, further if you try to factorize it, 9 can be written as 5 into 3 into 3. So 45 is 5 into 3 into 3. Now here this is the representation in product form. So 5, 3 and 3 are the factors of the number 45. So 45 is basically 5 into 9. 5 nines are 45. 9, when I further write its factors, I can write it as 3 into 3. So 5 into 3 into 3, these are the factors of number 45. Now let's see how to find the prime factors of a given number. We can do it in two ways, vertical arrangement and the horizontal arrangement. So here if I take the example as 36 and I want to find the prime factors of 36 using vertical arrangement, this is how I will do it. Draw a straight line and few sleeping lines in this manner and begin with the division. So we are basically going to divide 36 by 2. So after your division, 36 when you divide by 2, you get the quotient as 18, 1 8. So this is the number 18 that we are going to write it over here. 2 18s are 36. Similarly, factorize it yet further. 2 9s are 18 and 9 is a number now that will be divisible not by 2 but by 3. So 3 3s are 9 and 3 1s are 3 I have. So these are all the factors of 36, and when writing factors I will write it in the product form like this: 2 into 2 into 3 into 3. Now let's do the same thing using the horizontal arrangement. 36 I can write it as 2 into 18. 18 I can further factorize it. 18 I can further factorize it as 2 into 9. 9 can be further factorized as 3 into 3. So ultimately I have the answer here, factors of 36 as 2 into 2 into 3 into 3. Whether I use the vertical arrangement or the horizontal arrangement, I get the same answer. So these are the two methods in which prime factorization can be done. Besides the vertical and the horizontal arrangement, here is the tree diagram representation of factors of 36. So I have basically 2 into 18, and 18 I further wrote it as 2 into 9, and 9 I further factorized it as 3 into 3. So ultimately I'm left with these as the factors: 2 into 2 into 3 into 3. So this is how we find the factors using the prime factorization method. We can now begin with practice set 11 now. Factorize the following numbers into primes. The first example is 32. Divide 32 by 2. 2 ones are 2, 12 is the remainder, 2 6 are 12, 16 is the answer. So I'll write 2 into 16, 32. Again I can divide it further. 2 8s are 16, 2 4s are 8, 2 2s are 4, and 2 1s are 2. So these are the factors of 32. I'll write it as 32 is equal to 2 into 2 into 2 into 2 into 2. So these are all the factors of 32. Let's go to the next sum. The number we have is 57. 57 is an odd number, so it's not divisible by 2. Let's check if the number is next divisible by 3. Let's find the sum of the digits. 5 plus 7, I will have 10, 11, 12, 12. So 12 is the number divisible by 3. So 57 will also be divisible by 3. I'll just check 57 divide by 3. I get 19. So 3 19s are 57. That is what I'll write here. 3 19s are 57. Now 19 we all know that it is a prime number. it is divisible by 1 and the number itself. So I'll be writing 1 into 19 and I get the factors as 57 equal to 3 into 19. Let's come to the next sum now. 23 as we all know, it is a prime number. It cannot be divided by any other number besides 1 and the number itself. So we have to just 23 ones are 23. So its factors are just 23 into 1. Please write here into 1. Come to the next sum. 150 is what we have. So when you divide by 2, you get 75s. 2 75s are 150. Divide this further by 3. 3 25s are 75. 5 5s are 25 and 5 1s are 5. So the factors of 150 are 2 into 3 into 5 into 5. Let's move to the next sum number 5, where we have 216. 2 into 108 gives me 216. So again I'll divide by 2. 2 54s are 108. 2 54s are 108. 2 27s are 54. 3 9s are 27. 3 3s are 9 and 3 1s are 3. So the factors of 216 are, I can write it as 2 into 2 into 2 into 3 into 3 into 3. So these are the factors of 216. Let's move to the next sum, 108. 208. When I divide this number 208 by 2, I have 2 1s are 2, 2 zeros are 0 and 2 4s are 804. So 2 52s are 104, 2 26s are 52, 2 13s are 26 and 13 ones are 13. So the factors of 208 are 2 into 2 into 2 into 2 into 13. So this was sum number 7. 765, when you divide, it can't be divisible by 2 since it's an odd number. Try division using the test of divisibility for 3 and you'll find that it is divisible by 3. So you have 3 into 255 gives you 765. Again divide by 3, you have 385s are 5 17s are and 17 ones are, and that is how you get an answer 3 into 3 into 5 into 17. So these are the factors that we have for 765. Please find the factors of 342 yourself. We'll do the next sum, 377. 377 is a number divisible by 13. 13 29s are 377 and 29, as we all know, that it is a prime number. So 29 will be divisible by itself and only 1. So we have 29 ones are 29 and we are left with factors for 377 as 13 into 29 with just 2 factors. Let's do the next sum, 556. 559. Again, using test of divisibility for the numbers 2, 3, 5, 7, 11 and 13, you'll get to know that number 559 is divisible by 13. Let's see how many times it is divisible by 13. So I'll divide 559 by 13 and I get 4s are 52, 39 is the remainder. 13 threes are, and 43 again is a prime number, so I have just two factors here. 559 is equal to 13 into 43. With this last sum, we come to an end of practice set 11. Thank you.